Hello, everyone. Welcome to our Cosmic Thursdays. My name is Sinan Du, and I am in charge of education and public outreach in the Department of Physics and Astronomy at UCR. I'm also the organizer of this event. So I know some of you might have already stayed with us for a while. Thank you for your support. And if this is the first time you're checking us out, welcome. Regardless, we are very grateful that you're here with us this evening to listen to this exciting astronomy public talk. It is my pleasure to introduce our speaker today, Professor Laura Sellis, who is an astronomy professor here at UCR. Professor Sellis got her PhD from the National University of Cordoba in Argentina, after which she worked as a postdoctoral researcher in Europe. Afterwards, she moved to Boston as an ITC fellow in the Harvard University before joining the UCR astronomy faculty in 2015. Her research focuses on using simulations to study galaxy formation, dark matter, and cosmology. So in this lecture, she will be talking about galaxies in the nearby universe, which are galaxies that are relatively close to our Milky Way, and what they tell us about galaxy formation. Finally, I would like to thank our lovely volunteers today. As you can see, we have 4 UCR astronomy graduate students here joining us today in the live chat. They're all graduate students working in research fields that are relatively close to the subject matter we'll be learning about today. And all of them will be earning their PhD soon. So now I will let them introduce themselves one by one. Jess?
Hey, I'm Jess Stoppel. I'm a 4th-year PhD candidate here at UCR, and I study globular clusters and galaxy formation, and I'm super excited to answer all y'all's questions in the chat tonight.
Thanks, Jess. Garrett?
Hello, everyone. My name is Garrett Lopez. I'm at the end of my 2nd year as a PhD student at University of California, Riverside, and I study the early universe and dark matter.
Cool, thank you. Mingfeng?
Hello, everyone. I'm Mingfeng. I'm a 3rd-year PhD candidate here at UC Riverside, and I study how to use machine learning to infer the cosmology from the observation using simulations. And thank you.
Cool.
Welcome, everyone.
Yeah, welcome everyone. And last but not least, we have Nusha.
Hi everyone, I'm Nusha. I'm a 2nd-year graduate student here at UCR. My research is mainly on galaxy formation and evolution, and I would be happy to answer your galaxy-related questions today on chat.
Great, thanks everyone. And well, for those who are tuning in live with us, they will be the moderators for the live chat today, which you can see on the right-hand side on the YouTube page. We welcome all kinds of questions and also encourage you to engage in discussions. Because we have a large group today, so we kindly ask you to be respectful to each other in the discussion. So most of the questions will be answered by the chat moderators directly in the chat. The remaining questions will be relayed to Professor Sellis to be answered at the end of the lecture. So I guess without further ado, take it away, Laura.
Thanks, Sinan. I would also like to start by thanking everyone for making the time to be here. It's kind of unfortunate that we cannot really see face to face, but also, you know, the online format helps for people maybe a bit farther away to join. So we're excited to bring this talk today. I'll start by sharing my slides. Okay. And from here, we're going to go here. Let me make sure that, all right. So Sinan made an excellent description of my path before joining UCR, but for those that are maybe a bit late, let me describe it very quickly. I'm originally from Argentina. I was born there and I studied. I did my undergrad and my PhD degree in Cordoba, which is at the center of Argentina. And after that, I went to Europe for 2 postdoctoral positions, one in the Netherlands for 3 years, and then I jumped another 3 years in Germany for the Max Planck Institute. In 2013, I went to Harvard University as an ITC fellow. And in 2015, I made my final unlucky jump into a faculty position at UCR, and I have been there since. So while as a child, I imagine myself kind of like this, and actually that's how my mom also sometimes thought that I was going to end up. This is more or less how my friends in Argentina think that I look like when I work here, but reality is actually like this. So this is a picture of me a few days after joining UCR. And yeah, so our bread and butter is mostly computers, because what we do, as Sinan described, is a sort of theoretical galaxy formation. And that means that we build numerical simulations that mimic how galaxies form and evolve. Of course, any research that I do, it could not be done without my awesome research group. And you can see a picture here, it's a bit old. So some people have already graduated, but you have the names there. And the 2 of them, Jess and Nusha, will be answering some of your questions. They are absolutely amazing. So don't hesitate to ask questions. And we have Darren over here. He's an undergrad student at UCR. So that is enough for introduction, and we are here to talk about galaxies. So when we talk about galaxies, perhaps the first thing that comes to mind is the Milky Way. And you have here a picture of the Milky Way that is our own galaxy, the one in which we live, and with the background of the Joshua Park National Park. And you might be familiar with this beautiful stripe, of course. So what you're seeing here is the disk of the Milky Way, but because we live in it, what you see is basically a section of the disk. And you can see over here, all of this dust is metals and dust that are in the disk of the galaxy. And over here in the horizon is where the bulge is in this particular picture. But of course, the Milky Way is the only one from which we have this perspective from inside. There are other galaxies, and I will just start by showing one of them, that is the Andromeda Galaxy, that is our closest similar galaxy to the Milky Way. And we will see Andromeda coming back in a little bit. But yeah, so this is more commonly how we actually see other galaxies from outside, completely from outside of the galaxy. Andromeda is also a disk galaxy, so you could imagine that this is not too dissimilar from the Milky Way, except that Andromeda is a bit more massive, and the Milky Way is supposed to have a bar that Andromeda doesn't really. But of course, there are many more of these galaxies. And I wanted to start perhaps with a bit of perspective of how Andromeda looks like in the sky. So we said this big thing over here, this band of stars, is our Milky Way. And this is more or less how Andromeda looks like on a real scale on the sky. And for comparison, this is the moon, right? So the moon is more or less about a degree. So it's you see Andromeda is a bit bigger, it's a couple of moons. But there are also other objects here projected. You have another sort of more dwarf irregular galaxy. You have a nebula, or here you have a comet. And you see that, you know, without information on the distance, these things do not look so dissimilar. So historically, it took some time to understand what galaxies really were. And there was a famous debate between, there was two schools of thoughts. One saying, you know, galaxies are like, say, Andromeda, are their own island universes, right? Kind of meaning that they were like the Milky Way, but completely separate. And there was another school of thought that actually was defending the fact that they were actually part of the Milky Way. These nebulas were just part of the Milky Way, the same way that this one is, for example, or the remnant of a supernovae here, number 8. And that is because, you know, if you only have the projection on the sky, this is very difficult to assess. You basically need distances. And so once we could measure velocities and distances, we could really tear apart what an external galaxy is from things that are within our own galaxy, like, for example, a supernova remnant or a nebula of a young star. So what are galaxies? Galaxies are, for the purpose of this talk, going to be a collection of stars and gas that is tied together, right? That doesn't fly apart. And you have here pictures of many perhaps some of them famous, like this one that you have over here. This is the Sombrero Galaxy, and over here you have M87. So these are typical galaxies that you will find in high density environments, and we call them ellipticals or lenticulars. And those are galaxies that you can see are kind of featureless, so smooth. Some people say they are boring, but they are actually not boring at all. And those tend to dominate the very massive end of galaxies. Now, at the scale of the Milky Way, galaxies will tend to look more like this. There are disks, and this thing that you see over here is the bar, right? So this is the nucleus and this is the bar, and then you have the spiral arms. So we actually think the Milky Way will not be too dissimilar to this picture that you see over here. But of course, we don't know because we're within it. But this is our sort of reconstruction of how the Milky Way could look like. There are other spiral galaxies like this one, for example, that you can see that the spiral arms are not so well defined, more flocculent, and they tend to be smaller in mass than the scale of the Milky Way. So you have bars, no bars. Some of them will interact with each other, and you can see these beautiful sort of asymmetric tails are because galaxies will merge and sort of affect each other through tides. And this is one of the famous examples as well of two almost Milky Way-like objects that are coming together, and you see their stars are starting to interact. As you go down in the spectrum of masses, so say below the mass of the Milky Way, the morphology of these objects changes quite substantially, and you end up in the regime of what we call dwarf galaxies. So dwarf galaxies are galaxies of the scale of the galaxies like the Milky Way, but they are like 100 times smaller, or even thousands and even more, right? So they can be very tiny. And you have pictures over here in the sort of in the bottom left corner. This one is another galaxy. And then as you go down in mass, they tend to become a bit less well-defined. The shape becomes irregular. And so we call them actually dwarf irregulars because they just look like a bit like a nebula, but not so nicely. So the disks, the typical disks, disappear for the low mass dwarfs. And you will get, we will get to see more of this, things that are so faint that you cannot even see them. But they are there, they are galaxies, and they are being discovered even today. But of course, the galaxies cannot be introduced without saying something first on where do they live. So we will start by a very short introduction of what is our universe. And we will try to place the galaxies within that universe. So what we know of the universe is very little or very much, depending how you look at this problem. So on the left, you have a pie chart with what we believe is the energy and matter in the universe. And it's divided in mainly 3 components if you put these 2 together here. So the yellow and the blue is the things that we know about, and we call baryons, but it's basically the gas and the stars and the dust and things that we sort of, it's more familiar to us. It's made out of materials that exist here in Earth. So that is about 5% of the mass of the universe, and it's not really a lot, only the 5%, right? So on the stars, you can see it's really less than 1% of the whole mass of the universe. So what is it, the rest? So the rest are things that our best theoretical models seem to support, but they have not really been detected in the lab. Those components are two. One is dark matter. Dark matter, we don't really know what it is, but we know what it does. And that's how we can actually incorporate it in our theoretical models. Dark matter is a kind of particle that interacts with the normal matter, with gas or with stars, only through gravity. So we don't have to care about any other force but gravity. And so again, we are actively searching for this in laboratories, in the South Pole, everywhere. But the particular particle that makes up dark matter is not known yet. However, we know how it acts or how it affects the universe. And the other 73% of the budget of mass and energy comes from from something that we don't know exactly what it's made of, but we know what it does. What dark energy does is exactly the opposite of dark matter. So dark matter just behaves like mass, and it does some gravity and attracts things. Dark energy is more like a pressure. So dark energy is an anti-gravity, and it tends to expand the universe. We are still trying to understand fully what it is, but we can model what it does to the things that we can observe, like galaxies. So that's how we actually make this model that is called the lambda cold dark matter model. That sounds quite, difficult to believe. So you might ask rightfully, why do we believe on this model that is basically made out of things that we don't really understand? And the thing is, there are several clues that we are on the right path on describing the universe. And to me, one of the strongest evidences of this lambda cold dark matter universe comes from this picture. This picture is basically a picture of the baby universe. And what you see here is targeting the whole sky, but instead of looking, with a telescope or a camera, what you do is you use microwave, the microwave emission to take your picture instead of just optical. And what you see is fluctuations. Now, these fluctuations, anything that has a little bit more microwave radiation is in red, and anything that has a bit less will be in blue. So this is a map of basically is mapping mass differences in the very, very early universe. These differences are tiny, all right? So they look huge here because we have used a color scheme to enhance these differences, but actually they are, the difference between a red spot and a blue spot is only 1 in 10 to the 5 parts. So that is a 1 divided by 5 zeros. So the fluctuations are really, really small. Yet we can describe this. It doesn't matter really how, right? We do some magic and we quantify these fluctuations. And what you see here is in green is what the cold dark matter model predicts. You see these wiggles? And in red, you see what we actually measure out of this map. So again, it doesn't matter what this map is. I'm happy to explain it, but it doesn't matter. This is not important. What is important is that a theory that gives you this level of coincidence by chance, it would be very, very evil of the universe to do that. So the fact that the theory can predict something so complicated, it's not a straight line that we are, by chance matching. It's something that looks very complicated, and the data really supports this. It's one, at least on my opinion, one of the strongest evidence that this cold dark matter universe really cannot be too different from what we believe it is. So now, again, how do we go? What we want to do to build a theory of how galaxies form is to go from that picture of the baby universe to things that look so beautiful 13 billion years later, once the universe has grown for all the Hubble time. But to do that, I wanted to show you a little bit of how the nearby universe looks like. So you might be, saying like, okay, we have a few galaxies around. Now, how many galaxies do we have around? And the question is, the answer is a lot, as in like so many that we cannot show you how many there are there. But we can make a video of approximately 400,000 galaxies observed with the slow and digital scale survey. So let me just introduce this so you can actually read it. This movie that will start now will show you a fly through the 400,000 galaxies closest to us that we have. And what is important of this video is that this is not a simulation. This is real galaxies. And this fly through will show you a little bit how the galaxies distribute in sort of the first steps of our cosmic backyard. And I will, because it has music, I will try not to say much in between because it interferes, but I will try to pause and show you important things to look around. So let's go. Okay, so remember, each point that you see here is a different galaxy. So pay attention to the diversity of colors and shapes that you will see in this video. As well as you are flying through, you can see that most of the space is actually empty. And these galaxies will arrange in something that we call the cosmic web. That is actually like a spider web full of filaments, and these filaments kind of intersect and form knots where groups of many galaxies kind of are allowed to form. And you can see one of those groups, for example, here, but there are many, many more that are more massive. So let's continue this for a little bit more. Okay, so I hope you were able to see the filamentary distribution of galaxies. And I just wanted to point out, this is one of the knots over here. You see a concentration of a lot of points. All of them are galaxies that are in what we call a galaxy cluster. And there are typical correlations that you can see on the colors of the galaxies. For example, you see that the points over here tend to be on the yellowish red side of the spectrum, whereas if you choose a galaxy in a more empty space, say this one over here, for example, or anything over here, they tend to be blue. All right, so I will explain a little bit of those differences in those correlations. And I just wanted to mention before I put a little bit more of this amazing video that the Milky Way tends to live not really in a place that is this dense, but also not in the middle of nowhere. It lives in an intermediate environment that is kind of close to one of these filaments. So let's continue for a minute more. Okay, so I will just stop there. I can watch this video all day long. I really find it so amazing and giving you a perspective of the immensity of the universe that is, goosebumps. One curious thing about this video, you can find this video online, I think in YouTube, you can find it. It was made by an ex-postdoc in UCR. So Miguel Aragon Calvo, he actually put together all the images of these 400,000 galaxies and made the fly through. It's just actually amazing work. Okay, so let's recap a little bit then what was our question. How do we go from the picture of the baby universe to galaxies that we see today, like this one over here from
Laura,
yeah.
I'm sorry to interrupt, but I think the top menu bar of Zoom is blocking the title a little bit. Can you move it down to
I will
bottom
give it a
left?
try. Sorry, but it doesn't let me press anything without disappearing. I might not be able to move this.
Okay, then that's fine. Maybe if you could just recite the title of each slide.
Yeah,
that would be good.
it's unfortunate. Has this happened for other slides too?
Yes, sometimes it's blocking, sometimes it's not.
Yeah, sorry, this is a bug in Zoom. It doesn't let me because I can only press stuff here. I cannot move.
Okay, yeah, that's fine. Sorry to interrupt.
Okay, let's see if it goes any better now. Good. Right, so picture of baby universe, galaxies today. How does it come together? What is our theory of galaxy formation? So the idea is that, you know, these tiny perturbations that we discussed at the beginning, in the very baby universe, everything is quite homogeneous, but you have spaces with a little bit more mass and a little bit less mass. These inequalities in mass grow with time, and eventually they become so massive that they can collapse on their own. And then is when we say that a halo has formed. As you saw, most of the mass in the universe is made out of this sort of exotic dark matter. So that dominates whatever mass is in those collapsed halos that we call now dark matter halos. And a little bit of the stars and gas and dust that kind of comes with it because it gets dragged by the dark matter is what forms the galaxies. And they will sort of deposit at the center of that dark matter halo. So when you see a picture of galaxies like this one on the top right, what you should think about is this is only the sort of the frosting, so the tip of the iceberg of a much more extended and massive mass distribution made out of mostly dark matter that you cannot really see. So you are like, okay, fine, but you know, how do we know that there is really dark matter there? And so I will try to convince you, or at least I will show you the evidence of dark matter in several scales and in several ways. Perhaps the most famous one is the rotation curves of galaxies. And this is shown over here. This is a picture of one particular disk galaxy, M33, which will come up later in the talk again. So what you do is you put your galaxy at the center, and now you measure things as a function of distance. So at different points along this galaxy, you measure how fast this the stars and the gas is moving. That's basically what we call a rotation curve. And what you find is this green curve over here. So the velocity of how fast the things move increases, and then at some point just levels up. Now, what we know from sort of our dynamic and Newtonian physics is that the velocity of any object scales with the mass. So if you put more mass, you go faster. When you put less mass, you decrease. And then you divide by the radius. Okay? So now you measure this green line, and now you can say, well, but I know the mass, because the mass is what I can see. So I know the mass of the stars, I can measure that, and I know the mass in the gas in this galaxy. So what would happen if instead of measuring, I predict this based on the gas and the stars that I see? When you do that exercise, you get this yellow curve over here. And so you see that there is a huge mismatch between what you measure, well, the velocities that you measure, and how much you would estimate based on your knowledge of physics. So that difference over here is attributed to dark matter. Now, a different way of thinking about this is if imagine the velocity of the gas and the stars being this high, if it wasn't because of dark matter, this galaxy would completely fly apart. It could not be bound because it doesn't have enough mass to explain these velocities. So the fact that galaxies have not flown away, but they are there for basically the whole history of the universe, as you know, our observations of deeper and deeper into the universe shows us, says that this is not a transient, right? So galaxies are there, and that means that something is holding them together to move this fast, and that is dark matter. What is dark matter sort of in our own galaxy? I just wanted to give you a little bit of perspective. So imagine this is our sun. We are about 8.5 kiloparsecs from the center of the galaxy. Right, so it doesn't matter really what a kiloparsec is 1,000 parsecs, and a parsec is about 2 to 3 light years. So don't worry about the units because we're not so much interested in this. We're going to compare units and distances in the same unit. So that's what makes it easier. So right, we are at certain distance from the galaxy center. The disk of our own galaxy is about 20 on those kiloparsec units. So, you know, the sun is about halfway through the disk. There is another couple of 12 kiloparsecs on the other side. And now, what is the edge of the dark matter halo? It's about 250 kiloparsecs. So you see, it's about a factor of 10 beyond the disk. So once the disk of the galaxy ends, that is kind of where you feel comfortable now in your universe, then a factor of 10 more, and this is still part of the Milky Way. So this dark matter halo is much more extended and fluffy than the disk that we know of the Milky Way. And it's not only more extended, it's also more massive. And we have some numbers over here. The disk of the Milky Way is about 60 billion, but it's a 6 followed by 10 zeros. And we use the units of suns. So you just put many suns together, and then you get 6 times 10 to the 10 in the disk. Now, the mass of the dark matter halo is 2 orders of magnitude more. Instead of putting 10 zeros, you will put 12 zeros. And so it's much more dominant, not only on space and extension, but also on mass. How else do we know that this dark matter is there in the halo of the Milky Way? So a different tracer, if rotation curves are not something that convinced you, I can offer you a different tracer. And this comes from sort of the fossils of interactions of the Milky Way through history. So in the same way that I showed you that there were, for example, galaxies that were coming together today, and we can take a picture of that interaction. In the past, the Milky Way had many of these interactions as well. And some of them leave behind, as they are being, you know, sort of destroyed by our own galaxy. They leave behind a trail of stars that we can observe. And you have an artist's representation here of such a process in which you see this is the object with which the Milky Way is interacting with. And it has been stolen part of its stars, which now distribute in these tails that we call tidal streams. These tails, they go like, you know, one goes sort of ahead of the object moving, the other one trails behind. So it's a leading arm and a trailing arm. And these trails are going to mark sort of an orbit around the Milky Way. So let me show you a movie of how that process occurs. So this over here is a very simple numerical simulation. These cyan dots that you see here is simulating the perturber, so the thing that is interacting with the Milky Way. The Milky Way is at the center, but you don't see it. It's not shown. So it's only showing the thing that is interacting with the Milky Way, a smaller galaxy. So look what happens when you play the movie. Let me pause it over there. So this is kind of what I was saying. So your perturber is here, but whatever has been stolen by the potential of the Milky Way has a lot of gravity. So that gravity is pulling away stars from this perturber, and it's delineating these very nice tails. One goes ahead, the leading, and one goes behind, being the trailing arm. All right, so let me continue the movie. Okay, this guy over here is the perturber, and if you can follow it with the eye a little bit. There it is, and it goes for another round and another round. The simulation ends there. So basically what you see, this distribution of cyan particles, now they have left evidences or fingerprints of the orbit of the perturber around this, the Milky Way potential. This is exactly what you're seeing in this here. Now, these orbits, in the same way that the velocity was an indication of how much mass is inside, like with the rotation curve, an orbit, it gives you exactly the same information. All right, so if you know the exact orbit, you can now work out how much mass should be within each of these loops. So, so you could have such an orbit around the Milky Way. Okay, and so let me play this just once more so you remember tidal disruption. So now I will not pause it anymore. And orbits around your galaxy. Okay, does this happen in the Milky Way? Absolutely, and I will show you a picture of it. So these are stars from the Seaway survey. They are color-coded by distance. So you see over here, this overdensity of stars. You see that it's a bit brighter over here than in the rest of the map. That is the Sagittarius stream. So this is perhaps one of the earliest tidal streams discovered in history. Of course, we discovered it in the Milky Way because it's nearby. And it shows you part of an orbit, is an opportunity to see a part of the orbit of our own Milky Way dark matter halo. And so over here you have, again, this is a simulation, a reconstruction of how that would look like if we could look at the system from outside. Remember, we are inside the disk, so it makes things more complicated. But basically, if the sun is over here, the Sagittarius dwarf is not totally tidal disrupted. It still is, so there is some remnant, but these tails is what we are seeing in this Sagittarius stream. And by modeling this, we can actually calculate how much dark matter or how much matter is within these radiuses. And it's not enough, what we calculate is not enough, or it's not explained by the stars and the gas in the Milky Way. We need dark matter to explain the Sagittarius stream. And this is not the only one. The sort of the halo of the Milky Way is populated by many other structures. They're fainter. You have over here one of them, for example, the orphan stream. This is much smaller than Sagittarius, but it's exactly the same physical process. A small perturber or satellite came close to the Milky Way and started to lose their stars and left a trail on the sky that we can now go and measure to compute orbits within the Milky Way. So now that we are moving away from the disk of the Milky Way and into the stellar, into the halo, what else will we find beyond, say, Sagittarius stream? So over here is a collection of some of the most bright satellites of the Milky Way. What are these satellites? So you have the disk of the Milky Way at the center. What are these companions? These are actually tiny galaxies, galaxies of their own, but they are within the gravitational potential of the Milky Way. So they are orbiting around us in a similar way that the planets orbit around the sun. These galaxies that are galaxies on their own right, they're just smaller, they are orbiting around the disk of the Milky Way. So this is, I think I counted this, there's about 20, and these are, you know, what we call now the classical dwarf spheroidals. And those are objects that are very tiny, but they are relatively bright compared to, I will show you the tiniest galaxies in the universe, okay? So these are sort of intermediate mass, and we call them dwarf galaxies. Among the most famous, perhaps, are the large and the small Magellanic clouds. Those are the the most massive satellites in the Milky Way, and we will see them a bit more in detail later on. We have Fornax and Sculptor also. They're discovered, I would say, almost 100 years ago. So we know them well, and there are pictures over here showing you how they look like. This is Fornax, this is Sculptor, tiny galaxies, but still you can see them by eye. Now, here at the bottom is a picture of Seaway 2, which is one of the satellites that is not even shown here. We call it an ultra-faint satellite. And those are now many, many more. So these are 20 of the satellites of the Milky Way that we know. There are many more, at least 50 discovered once we count these ultra-faint dwarfs. These ultra-faint dwarfs, I'm showing you some of them. These were discovered in 2017, so quite recently. And you have the pictures here. You can't really see these guys. Horologium 1, Reticulum 2, Pictoris ones. You can see it only because we have shown the stars, member stars in blue. Otherwise, you couldn't see them against the background. So it takes up very clever techniques to discover these very tiny, tiny galaxies. And we don't know how many of them are there. We keep discovering them, like, you know, every once a month, somebody says, hey, there is here a tiny new galaxy in the Milky Way. And that makes this field of dwarf galaxies very exciting because we are still discovering them even within the halo of the Milky Way. And this is a bit of sort of how the discovery of these satellites have progressed with time. At the beginning, this is, you know, almost 100 years ago, they were Sculptor, Fornax among the brightest of the Milky Way satellites. And they used photographic surveys. You know, we were adding one every once in a while. And we knew about these 20, almost 30 dwarfs when I started my PhD. And now after that, the survey that you saw this fly through, this Sloan Digital Scale Survey, started to really uncover a mine full of these ultra faint dwarfs. And now the count is more or less 60 in the Milky Way alone. These ultra faint dwarfs are kind of sometimes difficult to differentiate from other objects that we know, like, for example, globular clusters. So what you have here is the size, okay, so how extended they are. And here is their magnitude, how bright they are. Bright things in the top, no, faint things in the bottom. And so what I wanted to show you is that this population of dwarf galaxies that are here in blue and in cyan, candidates, sort of merge almost with the population of globular clusters, right? So now disentangling what is a galaxy from what is a globular cluster becomes fuzzy. And so there is a lot of interest on this area of the plot. So things that could be a stellar cluster or things that could be a galaxy. And you're like, okay, but how tiny can a galaxy be? Well, let me tell you, over here in this sort of bottom area of the plot, this is about 100 solar masses, basically 100 stars, 100 suns. And just for a scale or for comparison, remember the number of stars that we had in the Milky Way. This is 60 followed by 9 zeros. So you see the diversity of galaxies in the universe is just so huge. And the Milky Way is not even one of the most massive, it's just a normal galaxy. And we are now finding things that have only 100 stars. So these ultra-faint galaxies are absolutely fascinating, and they are super dark matter dominated, and that's why a lot of attention go into understanding them much better. So what else is, so in the halo of the Milky Way, we're going to go from the tiny ones, these ultra-faint galaxies, to the most massive satellites still of the Milky Way, and this is the Magellanic Clouds. Magellanic Clouds, you can see them over here, they're in the south. So I grew up, actually, you can see them in the if you go to a countryside of Argentina, you can see them naked eye. So it's a pair of galaxies, they're interacting themselves, and they're losing gas. And that gas, again, boom, is now an orbit within the Milky Way potential. So you have here a better, so this is a real picture. This is from Australia, I believe. So the LMC, the Large Magellanic Cloud, has a bar itself. And this is the SMC, a companion of this galaxy. They are blue, They are young, they are forming stars. And what we know is that the LMC is moving towards the disk, is approaching the disk of the Milky Way from the south at this velocity, 300 kilometers per second. That in human units is a lot of miles per hour, okay? It's very fast. So this velocity, you can, again, any velocity you can now work out into how much mass should it be there to explain this velocity. And this is another evidence that the Milky Way has a lot of dark matter. Otherwise, we could not explain the very high velocity of the LMC around it. So in the last couple of minutes, I wanted to take you sort of farther away, even from the Milky Way. So we have been talking about the Milky Way and all the companions, all tiny dwarf galaxies around our own galaxy. But what else is there? So we can zoom out a little bit and enclose Andromeda. We talked about Andromeda at the beginning, but you see, people tend to say, oh yeah, Andromeda is our closest neighbor. It's not our closest neighbor. We have plenty of galaxies between, much closer than that. But it is our closest similar neighbor to the Milky Way, all right? So it's the next giant disk, if you want. So Andromeda, the same than the Milky Way, has its own collection of dwarf galaxies. And you can see some of them here, named over here. There are many more. And I just wanted to show you a bit of scale. So the Milky Way halo, we said, is about 250 to 300 kiloparsecs. The distance between Andromeda and the Milky Way is about 800 kiloparsecs. So say the halo of the Milky Way stops more or less here, and the halo of Andromeda also stops more or less there. So we actually believe that Milky Way and Andromeda are coming together to be interacting, like one of those pictures that we saw at the beginning. In the future, they will interact, and actually, if you run your future simulation enough, they will merge into a single galaxy. But for now, there are two, and each of them have its own collection of dwarf galaxies. So this is, again, our beautiful picture of Andromeda. You know, you can already see two of these tiny galaxies, satellite galaxies of Andromeda, M32 and M110. So Andromeda also has a collection of these tiny dwarf galaxies moving around in the same way that the Milky Way has its own satellites. Does Andromeda have tidal streams? Absolutely. We didn't know this, but say about 10 years ago, people decided to point at Andromeda and, you know, integrate for very, very long time to get what we call the stellar halo, because these tidal streams are very diffuse. So if you just take a picture, you see, you know, the bright side of the galaxy, but you don't really see the wealth of substructures and collection of tails of past, basically mergers and past interactions. This is a relic. It's like, you know, it's like digging for dinosaurs. These are fossil records of the history of Andromeda that is imprinted in these stars, provided you integrate for enough time. So you can see here, this is the giant stream in Andromeda, and you have many, many more. You have this one, for example, is interacting right now. You can see the tidal tails coming out. Right, so over here, M33 is sort of the equivalent of our LMC, of our Magellanic Cloud. M33 is the most massive satellite of Andromeda. I have a picture over here. It's a disk, and it's not only a disk, it's a perfect disk. It's one of the, we always use this picture when we want to show a beautiful galaxy. It's a disk, and it has almost no bulge. It has no, it's all of the stars are sort of co-rotating in a plane, and it's actually quite difficult to explain from theory point of view how to form those guys. Now, if I have, Sinan will get upset at me. I will only show you one picture of what else is beyond. I will stop here. So what we have been talking about is the local group, this tiny dot here that now you cannot resolve anymore. Beyond that, we have plenty of structures that I start to delineate this cosmic web that I introduced at the beginning. So our closest cluster of galaxies, say massive collection of galaxies, is the Virgo cluster. You can see it over here. And as you can see, again, the colors become quite red because they are old objects compared to the local group, that things look a bit more blue because it's young. And with the Virgo cluster, you have other structures like the Fornax cluster or Centaurus or the Hydra cluster, all things that are quite different from the emptiness of the local group. So I think I have run out of time. I would love to tell you more about these very high density environments, but we will leave that for a future talk. And now let me see if I can quickly take you to my concluding slide over here, showing you our cosmic backyard a bit and some highlights of the things that I have discussed. Thank you.
Thank you very much, Laura, for a fantastic talk. And if you have any questions, either for the chat moderator or for Laura, feel free to put it in the chat. But for now, we are going to answer some of the questions that has already been in the chat for a while. So the first question is from RWM Brain Drain, asking, knowing the ratio of elements in our solar system, is it possible for us to know what generation of matter we're made of? For example, are we the second or third, or is it possible to be the 7th generation of matter?
Oh, okay. That is an interesting question. I don't think I wondered that myself. Interesting. Yes. So this is the idea that, you know, all the metals and all the dust and even ourselves, anything that makes our world was generated within the stars, right? The universe starts being pristine with only, you know, hydrogen and helium, but now you have planets. So how many generations it took to collect all of this? The answer is, I don't know, but many. We're definitely not second generation, and we are not probably third generation. And so it's difficult to answer this question because the metals, once they are formed, they are not staying in place. Otherwise, we could attempt some modeling of this. But the thing is, you know, when the stars form and then they create all of these metals, then they explode. And when they explode, they generate winds. And these winds take the metals from the disk into the halo and even farther. So it could be that our material actually comes from a completely different galaxy from when, you know, the universe was smaller and things could travel more easily. So we don't know that, that question really with any precision, but it's definitely, it took many, many cycles to get to the complexity of the elements that form our planet today.
That's a great answer, Laura. And the next one is from Greg Edwin, asking how many light years away from the Milky Way does the video of 400,000 galaxies cover?
Oh, good question. So excellent question that I don't know the answer. Okay, so let me venture a number.
Or even order of magnitude.
I will venture an order of magnitude. Thank you, Sinan. That's much easier. So I suspect this is in the tens of thousands megaparsecs. And, you know, order of magnitude is the same of light years. So it's tens of thousands of millions of light years. So it's a 10 to the 10 light years.
Wow.
Okay, so this is really far. So just again, to have some idea of the scales, the local group is kind of 1,000 light years. It's not really, it's more, but it's order of magnitude 1,000. So this was going 10 to this, 1,000,000 times farther and more, presumably.
Yeah, that's already beyond my imagination.
It is really far.
Yeah, it is. Great. Next question is from Carmen Fragapane, asking, what are your thoughts on the satellite planes that have been observed? Specifically those discovered around the Milky Way, Andromeda, and Centaurus A. Are these satellite planes perhaps inflows from cosmic web filaments?
We have some very well-informed people in the audience.
We do.
Absolutely. I couldn't discuss any of these things. Satellite planes are fascinating. They're fascinating because we cannot explain them. So it's currently one of the perhaps most serious challenges, if you want, of the cold dark matter model. So for those that are not familiar with this, so, I showed you how the satellites were distributed around the Milky Way or around M31. Truth is, if you look at them closely, they are not randomly distributed. They are not spherically distributed. They tend to lie on a plane. So we have seen now that some of them are coincidence. Once you have the velocity, you know that they're just passing through the plane. They are not really belonging to the plane. But still, we have an uncomfortable tension with the sphericity that we expect out of cold dark matter. And I'm not saying that this rules out cold dark matter, but it has had many teams scratching their heads trying to understand the origin. And so, as Carmen is saying, inflow from this cosmic web, it could be, actually we have very important teams supporting this evidence. There is a little bit of a mismatch because you need a bit of fine tuning. In other words, the width of your filament through which these galaxies would be flying through is a bit too wide to explain the thinness of the plane. So sure, they could come from preferential directions in these filaments. That's excellent. But it's kind of borderline, whether we are convinced by that argument. Having said this, that is the best argument that we have. Cosmic flows within the halos, but it does require a little bit of fine tuning to explain how thin they are. So when they were only in the Milky Way, people was like, yeah. But there is some indication of this on M31, and now there is some indication of this in Cene. So yeah, we're starting to say, well, maybe we should pay a bit more attention to these planes, definitely.
Thank you, Laura. Next question from Sarah Faraj, asking, how far away from the center of the Milky Way is Earth? And have any attempts been made to get outside of the Milky Way to view it in whole? Is it even possible?
Mm-hmm. Good. So, Sarah, the distance to the center of the Milky Way is so huge that is the same than saying the distance of the sun. Okay, so the sun is about 8 to 8.5 kiloparsecs. So that is 8,000 parsecs and about a factor of 3 more light years. Okay, so it's about 24,000 light years or something like that. So a lot, but for astronomy, distances not so much. But way beyond what we know, that is, say, the solar system, it doesn't even use parsecs anymore because it's too small for that. So having said that, can we get out of the Milky Way? Not with any current technology or whatsoever. Okay, so the farthest away, so we have, NASA has launched this probe, the Voyagers, outside the solar system. Is right now, like after 30 to 40 years, reaching the edge of the solar system. That's nothing compared to the distance that we have from here to the center of the galaxy. So current technology will not propel us out of the Milky Way by no means. Also, not even to the closest star, Proxima Centauri. That one also is 4 kiloparsecs. We cannot get there. But we are looking for, young minds that might be in the audience that will come up with an amazing new technology that will take us outside of it. That would be fantastic.
Totally. Great. Thanks for that answer. Another question from Greg Ewin. Are there any other theories to explain the indirect evidence of dark matter? Why couldn't the properties associated with dark matter just be the characteristics of space-time itself?
Excellent, Edwin. Thank you. Yes, there are many more theories. Of course, people is not happy with this. Yes, there is dark matter, but we cannot find it, right? So there is a lot of people that actually is skeptical, and it's great. We need in science, you need several teams to be working on opposing hypothesis. As you suggest, it could all be, so there is one or a couple of families of theories in which they say, well, It's not that there is more mass. What happens is we don't understand gravity well enough. And so what happens in these theories like MOND, for example, one of them, or we call them FOR, it doesn't matter the name. So in these theories, what happens is gravity behaves differently in areas where the acceleration is low. So now, by modifying gravity, you can basically explain the behavior of the rotation curves. But the issue is that there are, so this theory can explain quite well the rotation curves, but it fails in other evidences of dark matter. For example, gravitational lenses, something I didn't have time to go into. So there are competing theories where there is important people pushing knowledge on that direction, but they are still having to solve some loopholes that seem a bit better explained by the CDM, the cold dark matter scenario.
Yeah, thank you, Laura. And last question also from Greg. Maybe this can be a short one. The Andromeda Galaxy looks to have a slight wobble. Did it interact with another galaxy in the past?
Yeah, absolutely. Yes. Thank you for that question. The cold dark matter universe, this theory of how galaxies will form, predict actually a lot of interactions, plenty. So it's not uncommon once you start looking at the galaxies deep enough to see these tails, and they tend to suggest past interactions. One of them in M31 has been with M33, the triangulum galaxy, the perfect disk. So that interaction is supposed to have happened not too long ago, and as a result kind of creates a wobble in the disk, or a little bit of stars sort of kind of misaligned. And by studying that, the idea is that you can reconstruct the past history of galaxies on the Milky Way or M31 or whichever other one.
Great, thank you very much, Laura. And I know we're already at 7:30, so I would like to thank everyone again for staying here towards the end of this lecture. And before letting you go, I would like to quickly just have a plug for UCR Astronomy. You can easily follow us either on social media, for example, here on Facebook, if you just type Astro UCR, this is the page we have. So we're going to post all the scheduled events in the future here, where you can see, we have a virtual stargazing in August, and we also have another Cosmic Thursdays lecture in August, talking about possibilities of life beyond the solar system. And of course, we also have K through 12 sessions specifically designed for students. And we also have a community outreach website page that you can check out. It's very nicely designed, and all the scheduled events can be found here. So you can see this is all the lineup of events that we have in August. So we have 4 sessions there. I will also post the links to these pages right now in the chat, so it's easier for you to grab. I would like to thank everybody again for joining us. I think this concludes our lecture today, and we would really appreciate your feedback on how we did today and what we could do better. To that end, I will be sending out a survey for everyone who registered tomorrow. So if you could kindly take 2 to 3 minutes to fill out the survey for us, that would be much, much appreciated. So the survey is going to be completely anonymous, and we will only be seeing statistical results and also your comments about our program. So with that, I hope everyone enjoyed the lecture, and we hope to see you again very soon.
Thank you, everyone.
Thank you. Bye.